Okay, good morning. Today we're going to be looking at centripetal acceleration. So, quick recap. We want to think about angular displacement. That's one term we'll need. So, angular displacement is if we have this bung on a string going around, we use the symbol theta for angular displacement, and that is an amount of angle that something's moved through. So if it's moved from this position I've just marked there, that would be the angular displacement. Angular velocity, omega, that's how much angular displacement it's doing per second. So I could write that as something like omega over little t, so if it moves through an angle in time t, it would be omega over t. I could also say if it does a full circle, then obviously it's covered 2 pi radians, and it will do a full circle in its time period, so I can also say omega is 2 pi over big T, where big T is the time period for one complete revolution. And then linear velocity, this object's travelling with circular motion, so at this instance here, it has a linear velocity, that's how much actual distance it's covering each second in that direction. Later on, let's say when it was at this position here, again it would be going tangentially, so that would also be linear velocity, and that linear velocity will stay the same for everything you cover at A level. We always do uniform circular motion, so the rate of linear velocity and indeed angular velocity will never change. Today we're going to look at centripetal acceleration, so we're going to take things a little bit further. Now, you've probably heard this term a lot before, centripetal force. The definition of it is any force that causes, and that's really important, if the force has to cause the circular motion, then that is a centripetal force. Now, big problem that a lot of students have. A lot of people think that if something is going in a circle, then magically the centripetal force exists because it's going in a circle. That's not the right way of thinking of it. Something goes in a circle because of centripetal force. It's a centripetal force that causes motion in a circle. And there's lots of different types of centripetal force. So if we take a Ferris wheel here, you've got these individual cars over here. Well, in this case, the centripetal force will be tension in the metal of the Ferris wheel. So it's causing it to be dragged around in a circle. If I have a car going round a roundabout or round a corner, well, there's friction between the tyres and the road. So that friction is causing the centripetal force, or it is providing the centripetal force. So centripetal force is never just a single force by itself. It's always another force that is providing centripetal force. If I have a plane going round, well, aircraft have lift from the wings. So in this case, there's lift. Now this is where it gets a little bit more complicated. For an aeroplane, obviously you've got lift from the wings acting upwards, and there will be a component of that. If I call that lift horizontal, there'll be a component acting towards the center of the circle, and in that case, it's the horizontal component of lift that is causing a circular motion as that plane kind of does a circle in the sky. Again, you think about something like a fidget spinner that's spinning around here. Here again, because this is a solid object, that will be tension in the object, pulling it towards the center. So, key thing, it's the idea that it's any force. So it could be friction, it could be tension. Those are the two most common ones. Sometimes we have lift, sometimes we have gravity. We'll go through those more specific examples as we get a bit further through the course. But I need you to get that if it's going in a circle, that force that's making it go in a circle is called, it happens to also be called the centripetal force. You don't get something going in a circle first and then centripetal force appears. If you don't have a centripetal force, you don't get circular motion. And again, as we get further through the course, we'll explore cases where that happens. One last example, the planets. Obviously the planets all orbit the sun. So from Jupiter's perspective, it is gravity. So gravity is another pretty common one that we will deal with. Now, what we need to do is we need to be able to derive this equation. Well, actually, no, you don't need to, but it's useful to know how it's derived. You don't actually need to derive it. What you need to be able to do is use the equation that we get to. But I think it's helpful to be aware of where it comes from. So I found this great example online. It's by Nathan Smith. I don't know who he is, but he's made a nice simulation here, and I'll link this in the video description. But what you can do here is we can explore an object travelling in circular motion. So what I have is an object here, and it's got linear velocity here. So it's got linear velocity v2 after it went from linear velocity v1. Now, because this is going with uniform circular motion, the velocity is never, so the speed is never changing. So the magnitude of these two velocity vectors, that isn't changing, but their direction obviously changes over time. So the idea is over here we have it at one instant in time, and over here we have its position at another instant in time. So it's kind of rotating through a bit of space. Now, over here on the other side, we've got a vector triangle. And as you know, we can say that essentially, as it goes through this circle, at instant t1, it's got linear velocity v1. Sometime later, it's got linear velocity v2. Now, we know that acceleration is final velocity take away initial velocity. So in this case, that will be v2 take away v1. So if I was then to draw that as a vector triangle, I would have v2 like that, and then I would want to take away v1 from it like that. And what I'm left with is a resultant vector that goes from v2 to v1 like that. Sorry, I said acceleration. That's obviously not acceleration. That should be change in velocity, because I can say acceleration is change in velocity over time taken. Okay, so this will be my change in velocity. And I haven't drawn it brilliantly here, but the simulation's quite good at showing that what it looks like. And look, as I move it around, look at where my change in velocity is pointing. Delta V always points towards the center of the circle. Now you should remember that from IGCSE. We know that for an object going in circular motion, we can say that acceleration is always towards the center of the circle. Now, there are loads and loads of different ways that we can go around now proving the magnitude of this. And if you type it in online, you will see a whole bunch of different approaches. I'm going to use one that I quite like, because it doesn't need calculus, so it doesn't need differentiation or integration, which is nice, and it ties in with what we've already learned. But there are loads of different ways of doing this, which is quite cool. That's one of the fun things about physics, is there are often multiple ways of getting to the same solution. Now, what I'm going to do is I'm going to say, well, okay, in this instance, I've gone from v1 to v2. So I have moved through an angle theta. Now, as I've moved through that angle theta, I can say, well, by similar triangles, this is also angle theta as well. So now I've got that delta V is here. So what I want to do is I want to find the magnitude of delta V. If I can find the magnitude of delta V, then I can put it into this equation here, and I can start to get acceleration. So if you look online, there's about 20 different ways you can do this. They all come from different approaches. Some use calculus, some use small angle approximations. I'm going to do the one that's only needs A-level, GCSE level maths, because I know not all of you take A-level maths. It means it's not always the most satisfying answer, but it does work. If you don't like this answer, look up others. There's loads of other ways you can get to this solution. So I've basically got a triangle that looks like this. Now, what I'm going to say is, if you remember back to last lesson, if I treated this as an arc, then I already know from my previous work that the arc length will be the length of, if it's centered on here, that would be v theta. Because for a general segment of a circle, it's got radius here, and this would be arc length, and that would be through theta. Now I can say, even though this is a straight line, I can say, well, as theta approaches 0, it's only a tiny little change in angle, this arc looks more and more and more like a straight line. So I can say, for a small angle, I can say delta V is v theta. So that would be kind of just the magnitude of the individual velocities, because we said that the velocity isn't going to change, the magnitude of velocity doesn't change because it's uniform. So I can say that delta V is v theta. Now, since I know that acceleration is delta V over theta, I can say therefore acceleration is v theta over however long that takes. But let's think back to what we said earlier. Earlier we said that angular velocity is my change in angular displacement over time taken. So what I can do is I can replace this theta over t with omega, and I get v omega. And that's our first key equation. This one you need to remember. You don't need to know how to derive it, but you do need to know that angular acceleration is v omega. Now, I've got some other equations that I know. I also know that angular velocity is v over r. That's something that we derived last lesson. So I can replace this omega here, and I can say that this becomes v, and I replace the omega with v over r, so that would be v times v over r, so that is v squared over r is also equal to acceleration, and that is another key equation that you need to know. And there's one more way that I could rewrite that. The third way that I could rewrite that is I could say that acceleration is r omega squared. And I can do that by getting rid of v from this case, so I can say that from here v is omega times r. So if I replace the v in this equation, that would be omega times r, omega squared r. Now these three equations, you can learn one of them and figure out the others by substitution. I would say it's probably easiest just to learn all three of them. The final phase is then to say, well, what about the actual magnitude of the force? If we think all the way back, we kept saying that centripetal force itself, that's a force that makes things go in a circle. So how do we find that? Well, the good news is Newton was always correct, so force is always equal to mass times acceleration. So in order to turn these into forces in all these cases, I've now got acceleration, I've got acceleration, I've got acceleration. So I can say that centripetal force is equal to m omega v. Yeah, v omega multiplied by m, I get that. I can also say it is equal to m v squared over r, or I could say that centripetal force is equal to m r omega squared. These three equations are also really key, really important to use. Which one you use often depends on what you're being given. If you're given something that's where you've got omega, obviously you just use this form of it. If you don't, then you can pick other forms in order to work out what you need for a given problem. And there we have it. So these are the key things for you to remember. This is probably the most common form of it that you will see. F is mv squared over r, but you also want to use the a is omega squared r, or f is omega squared r times m, or f is mv squared, well, so it's the same one, mv squared over r. So learn these, get familiar with them. For your actual A-level, you just need to know these equations, but I do think it's useful to know how they are derived, because it's good practice of what physics is like.